Okay, so thank you very much for the invitation. I'm glad to give this talk this afternoon. Novel experience for me. I have given talks to a screen and I have given talks in not so full rooms. I'm today giving this talk from a virtually empty building, so that is really a novel experience. So, but I hope I'll be able to entertain you through the next couple of minutes and in this times. So I choose as a talk towards Exascale Hyperbolic PDE engines. Are we skating to where the puck will be? And sorry, let me just, how do I advance So the quote, of course, is from the famous skating professional Wayne Gretzky, who once said that he is not skating to where the puck is, or the puck has been, but he is skating to where the puck is going to be. And translated to the exascale world, this means, okay, we have to do assumptions on exascale HPC, how it's going to be. So this is very much kind of closing in. But when we started out with the projects I will be talking about, that was about in the year of 2014, many of these assumptions were really assumptions of where we should be going, and where these assumptions were often quite coarse scale. And some of these things I want to address today and talk about a bit of experiences is so that we can no longer rely that if we just distribute work equally to the screen, to partitions or so, that this work will be executed in the same computation time as well, because computation time can vary a lot on hardware these days and can be unpredictable. We have to deal with the problem that moving data becomes more expensive. We have to be aware that cores and nodes might be crashing throughout simulations. And so one question, if you develop software, is that so will we keep on developing particular codes, one code for one problem, or can we make that more general? And actually, I have examples in this talk from both sides of the picture, both a single purpose code and a multi-purpose engine. So the agenda of my talk is very much dominated by projects and software projects that we've been doing in the last years. I want to acknowledge especially the CHEES, European Center of Excellence, in which both codes, ExaHyPE and SeisSol, are further developed. At the moment, ExaHyPE was developed as part of an Horizon 2020 project, and SeisSol was also funded by a couple of projects in the last year. SeisSol, with which I will start, is an extreme scale software for multi-physics earthquake simulations. It's an open source software. You can find everything on www.seissol.org. And so it's developed primarily by two groups in Munich, the Department of Geophysics at the Ludwig-Maximilians University of Munich, led by Alice Agnes Gabriel. So they are working on the seismology challenges, and most of the pictures stem from setups that they've been doing. And my group is at the Technical University of Munich, working on the HPC aspects and software development. And I also want to acknowledge lots of former members who've been working on the code and who are no longer present as a picture, at least in this slide. So SeisSol is computing dynamic rupture problems, so-called dynamic rupture simulations. So we model faults explicitly as surfaces, 2D surfaces that can have branches, that can have complex geometries. So two examples I've given here. One is from a simulation of the Landers earthquake from 1992 in California, which is featuring branches in the fault zones, and there can be effects like that earthquake rupture starts on one part of the fault and then is transported to other parts of the faults. And another example is the Sumatra earthquake on the right picture from 2004, which led to the Indian Ocean tsunami. And there, a lot of the challenges in terms of modeling stems from the shallow angles, how the subduction zones meet the complicated topography of the ocean floor, and also we have tried to model branches in the fault as good as we can. So SeisSol deals with all this via adaptive tetrahedral meshes, who are kind of able to deal with the complex geometries. And we're addressing the seismic modeling with a high order discontinuous Galerkin method that features so-called ADER high order time stepping. So one example that I want to feature is a bit more closely is the simulation of the Sumatra earthquake as a seismology challenge. So the model that we had for this earthquake actually extended in terms of the computational domain over the entire Indian Ocean, as you can see in the center picture. So the rupture itself extended over more than 1,500 kilometers. That's a distance, if you relate it to Europe, from Munich to Helsinki. So that's really a huge earthquake. And you can see that kind of illustrated in the left picture. Yeah, and there were several aspects of the complex geometry modeled, like the shallow angles in the subduction zone. There's a layered material on the subduction zone, and we had a couple of splay faults. The duration of the earthquake is a challenge, Sam, that was nearly 10 minutes. So due to the adaptive refinement, there were lots of very small elements, especially at the complicated features of the geometry. And so local time stepping running the smallest cells also at much smaller time steps than the bulk of the elements was a key algorithmic feature of the simulation. In terms of HPC, so we had about, the largest meshes that we were using for this method were about 200 million elements. If you do that at order 6 accuracy, you have about 500 degrees of freedom per element. So that leads to 100 billion degrees of freedom in the entire simulation. So the largest showcase run that we did on that was on the full SuperMUC machine back then. That was 86,000 Haswell cores, and it ran at about 1 petaflop back then. That was a 3 petaflop peak machine, so it's quite good peak performance as well at this type of scaling. So one of the impacts that we hope to get with this simulation is to better explain the generation of tsunamis. So from the earthquake and from the dynamic rupture simulation, you obtain the uplift of the ocean floor in a time-dependent fashion. And this uplift is then imposed as an initial condition, actually as a time-dependent initial condition on the tsunami simulation. And in these pictures, you have 2 simulations of the resulting Indian Ocean tsunami, which are kind of similar, but actually do have slight differences in the tsunami signal, actually, which you can see a bit better in this overlay with measurement data of a satellite. You have in red and orange the 2 different simulated tsunamis, and they actually differ in the earthquake model that you have at the beginning, whether you consider plastic deformation in the material response near the fault. So I want to highlight, especially on the HPC and algorithmics aspect. So if you look closer at the numerics of SeisSol, mentioned it's a high order discontinuous Galerkin method, but you can express this in the way that it's given on this slide, basically entirely as matrix operations. So all of the caps here, capital letters here, are matrices. You have matrix chain multiplication as the key steps, and this is the key part that you want to optimize in each element. And out of these several optimization steps that we performed on SeisSol, actually there evolved yet another tensor toolkit, as Carsten Uphoff, who was the main author on this, called it in the end. YATe To is a code generation utility for small matrix and tensor chain products. So what you do, you write down your matrix or tensor schemes, the element local algorithms in Einstein notation, which is very widespread notation. And then you can more or less mimic this notation directly in a kind of domain-specific language, which is based on Python. And you can write the indices as Python indices and formulate your chain products in that way. And YATe To will generate heavily optimized kernels for these chain products, which can then be executed in the software. So one of the features that you have in this chain compilation of kernels is that you do several steps of optimization of this chain product. So for example, you find the best possible execution order, so-called strength reduction, the best possible memory layout, whether you should have row major, column major for the intermediate results, for example. Also, the code generator will find index permutations that speed up performance. So that is, to some extent, established procedure in tensor software and tensor toolkits, but very often these tensor toolkits stem from different applications, and they more kind of focus on large tensors and that lead to large matrix operations respectively. So for SeisSol, all the matrix and possibly tensor operations are element local, so you have different sizes, like the number of quantities in your PDE, typically 9 for SeisSol, or the number of degrees of freedom per element, so it's kind of the integration point of your discontinuous Galerkin method, can be around 50 for a typical production order. So we translate these tensor and matrix operations with a matrix multiplication backend where we use libxsmm. So this is a highly efficient matrix multiplication backend, which is developed with lots of support from Intel. And so this is responsible for the high gigaflops rate that we want to achieve. Yeah, here you see in the picture just an update, an example that also if you have sparse matrices of sparse tensors, YATe To will automatically find an equivalent sparsity pattern that can further reduce the amount of operations in your computations. So this is a performance collection. I will not go into detail about the gigaflop numbers. What is interesting here, so you have a dependency of the order. So with increasing order of the scheme, the performance gets more and more computation bound. So the switch over starts from order 4 and then 5, 6, 7 get increasingly computation bound. Also, you have here the numbers for 16 or 32. So that is if you are doing fused simulations, so you are running 16 simulations at a time. So this offers you additional optimization opportunities that you don't have so much for a single optimization, and so you're getting higher performance for the runs. Also, you see that code generator supports both single precision or double precision. One of the big other algorithmic optimizations that we did in the last years was local time stepping. So the ADER time integration basically allows an element local time step. So elements can be advanced individually based on that their neighbors have already reached a similarly advanced time step already. And the numerics of this is well established, was already available in 2007, already implemented. But Advancing individual elements individually is an implementation and scalability nightmare. So getting this done in HPC fashion with high efficiency is really hard. So the first big success here was in 2017 when Alexander Boyer introduced a cluster-oriented local time stepping, and clusters here really are illustrated in the top pictures. So that are not necessarily compact clusters, but especially in the right picture, there can be stray elements with, for example, very small time steps that can be located all over your domain. All these elements are integrated in the individual cluster and are advanced at the same time step. So the full integration of local time stepping with the code generation and the dynamic rupture procedure was done in 2017. And that was actually a big step in getting the performance that we got for SeisSol. So this is an example of scaling runs or scalability. So it's all strong scalability experiments on 3 different machines. The blue one is the Cori supercomputer, was a KNL-based machine. Red and black are Haswell-based machines there. Shaheen in Saudi Arabia and Supermuk in Munich. And you see that this scales also for local time stepping, which are the solid pictures of global time stepping is the hollow symbols. So this actually scales beyond to several thousand nodes. And it gives a huge impact. So that's very shortly on the second picture on the time to solution. So this is the extrapolated time to solution for the Sumatra showcase and the 220 million element scenarios. Here you can see that the simulation time is reduced from days and weeks down to in the range of tens of hours. So 13 hours was the duration of the largest full machine production run. So this is some late work on improving local time stepping. So we are working on the shared memory parallelization particularly. And there we are reaching with the current parallel 4 on the clusters, we're reaching scalability limits if the clusters are small. So we're going for task-based parallelization. But this is particularly a problem if you have NUMA style architecture. So you need NUMA support for OpenMP, and that has just recently been kind of done by a group of Aachen University. And here you see some results with and without NUMA support for various task granularity. Another part, this is very fresh work we're currently working, is kind of to make the logic of the local time stepping a bit easier to swallow in the programming style. And here we are working on actor and finite state machine approaches, which is just an illustration here, which is used to schedule the local time clusters. Some of the work in progress, further work in progress for SeisSol is that we are currently extending the material models quite heavily on all fronts. And there's also been a lot of work on the I/O capabilities, how to get better models in there. And we are working also on a GPU port at the moment. So with that part on SeisSol closed, I want to have a look at a second software that we are developing that is called ExaHyPE, stands for Exascale Hyperbolic PDE Engine. And yeah, the software is again open source. You can find it on ExaHyPE.org. And so ExaHyPE was produced in a joint project of 7 partners in the Horizon 2020 project. I sketched the partners and the names here, so I trust that you can read through these offline if you want. The goal of ExaHyPE was to do a PDE engine in the sense of a game engine. So we're using fixed numerics and mesh infrastructure, but we want to stay flexible with respect to the PDE that is actually solved at the end. So we are again using a high order ADER DG variant, but which now works on tree-structured adaptive mesh refinement grids, so that is octree type grids. It's using code generation in a heavy wave to achieve high performance on nodes and multiple nodes. And in contrast to the SeisSol numerics, it's addressing nonlinear schemes as well. So if you're doing a discontinuous Gherkin for nonlinear problems, you require a limiting procedure, and there we use so-called a posteriori limiting that combines DG with a finite volume scheme that is robust for nonlinear effects. So here's a couple of examples that we are developing or have developed in the ExaHyPE Engine. So that ranges from complex astrophysics equations like simulation of neutron stars. Seismic wave propagation is again a big application, but there's also lots of examples from fluid dynamics, as you see in the bottom corner. So shallow water turbulence, cloud formation in kind of atmospheric physics sense, or the picture to the right is a flucture interaction, fluid structure interaction scenario. So you need to imagine that these white dots are actually rotating, and they are driving a fluid, a complex compressible fluid with shocks moving, and that is done by a so-called diffused interface method that's treating the complicated geometry via a color function. So ExaHyPE solves, in general, systems of hyperbolic PDEs. They have to be given in first order form. So we have a template PDE that is sketched in the equation that you see on the slides. And so a key component of the ExaHyPE engine is a so-called toolkit and code generator. And this basically provides 3 levels of abstraction for application experts that are basically relying on an API, where you need to implement the flux functions F, the non-conservative fluxes B, the source terms S of the PDE, and so on. And then you have kind of interfaces for algorithms and optimizations expert who work on the task-based implementation, for example, or on the key kernels of the algorithm, or just do highly hardware optimized optimizations such as SIMD parallelization and so on. So both the toolkit and the code generator are actually based on the Jinja 2 web templating engine. So here we use code generation capabilities that are established, but in other application areas. So this is a cartoon of the software architecture of ExaHyPE. So the cyan or blue parts, PDE terms, ExaHyPE specification file. This is what actually a user of the engine would provide. So you have to create a specification file that says, okay, what's my computational domain? How does my PDE system look like? Does it have nonlinear terms, for example? And then in which order of discretization do I want to use? And then the ExaHyPE toolkit would create a tool code and application-specific templates where you need to fill on your concrete implementations that the engine cannot know. So that is how are the flux term, how are the fluxes computed, how is non-conservative products computed. You would also have to provide code to compute eigenvalues, because these are later needed for components of the numerics Riemann solvers for the finite volume parts and DG parts, for example. Yeah, and the user solver that is created by both the toolkit and the user is then based on the ExaHyPE core, which has all the optimized kernels. And this is again based on Piano, which is the framework that does the data management for the simulations, and this is responsible for all distributed shared memory parallelization. So this is again an example for an application and of the elastic wave equation and the concept of seismology. Here, this is seismic wave propagation with complex topography simulated. And here I want to showcase some optimization steps. So the most time-consuming part in the ExaHyPE engine is the so-called space-time predictor. And we had, over the time, 4 stages of implementation, starting from a generic implementation via a so-called loop over gem implementation of all the tensor operations that we have based on the libXSMN backend again. And then we saw that the straightforward implementation suffered a lot from memory stalls when the L2 cache actually was not sufficient to hold all the element local data anymore, which happens if you go to high order and lots of quantities in the PDE. And so there were 2 algorithmic optimizations doing a dimensional splitting of the CK scheme used to compute the space-time predictor, and then to actually switch to an array of array scheme. So we do have the classical array of struct, where the struct of arrays conflict in our engine, and we kind of solved that to actually prioritize one of the typically 3 space dimensions as we had as the fastest running index, and that allows us further vectorization at a, I would say, mediocre overhead for programming and complexity of the code. So here is performance experiments and comparisons. On the left, you see for the 4 steps the massive increase in vectorized operations that you can use. So on the bottom right, in the 4th stage, kind of 80% of the vector instructions are 512-bit vector instructions, and nearly all of them, or only a few of the red instructions that are scalar are still left here. And you also see that in the available performance that is increasing to more than 20% of available peak in the right plot. And the dimension splitting scheme that I mentioned on the previous slide is basically responsible to reduce the memory stalls that we measure in the cache usage. Another area for optimization of ExaHyPE is tasking. So the shared memory parallelism of ExaHyPE shares on Intel TBV tasks. The space-time predictor tasks that I mentioned do an element prediction of the solution in each element. So these are purely element local, so they can be spawned in an asynchronous way. They are compute heavy, so they are ideal to kind of work with. And we actually implemented an infrastructure to allow us to offload these tasks beyond the borders of an MPI rank or a compute node to different ranks, different memory locations, compute them there, and get the result back. And for once, this allows us to deal with load imbalances, even in a dynamic way. So we can migrate tasks if, for example, ranks and compute nodes have to, are decreasing their performance due to overheating or whatever other reason, or because they are close to failing or so. So in that sense, we can deal with load imbalances imposed by external influences, not coming from the numerics itself. And actually, here you can see the 2 charts how, for example, a diffusion-based task offloading in the left plot would react to a sudden load imbalance and more progressively kind of put tasks to another compute node. So another area where we have been working with this offloading of tasks is actually to go for team-based resiliency with ExaHyPE. So that relies on an infrastructure that was realized at the University of Durham. That's called TMPI, and TMPI replicates all MPI ranks of a MPI simulation. So you have K teams of R ranks, and as you can see in the picture to the left, so ranks between ranks between teams actually exchange heartbeats among their replicas. And these heartbeats allow you to detect when another team is falling behind with a simulation. So in the right plot, so this is kind of a artificial study where one team is slowed down, and you can actually see the time between the heartbeats, and from this time you can identify which rank is actually slowing down, and you can react to it, for example, by migrating load away from it. So one of the latest results that we have on that is that if you have replicated simulations, and if you can actually share task out between the replicas, you can have, as long as everything runs well and no replication is necessary, you can actually share task outcomes between the replicas, and in that way don't compute everything twice if you have a replicated simulation. So you can do full redundancy, run 2 or 3 teams of simulations in a resilient fashion, but you don't pay twice or 3 times the CPU hours for that. So in our studies, we got something like a 1.5 speed up for 2 ranks. So that means you have something like a 30%, roughly 30% increase in total CPU hours for this replicated simulation, and not a 100% increase. So this is my summary slide. So are we skating to where the puck will be? So my answer to that is I really don't know. So it will still be to be decided in the next years. So I showed a couple of reactions that we did to the challenges of Exascale that we think will happen. So we're working a lot on engine concepts and code generation to balance this tailoring versus general purpose thing of software architectures. We have developed reactive load balancing and task offloading scheme for this load balancing and dynamics schemes. And yeah, we need to optimize usage of memory hierarchies for the moving data restrictions. Yeah, and we started to work with replication-based resiliency approaches. Yeah, so I have a couple of acknowledgements that I will not go through on the slide. And I also have added citations to the rest of the slides, but I think the slides will be offline, so you can go through that if you are interested. So thank you very much for your attention. I'll be happy for questions.
Thank you very much, Michael. So we have a few minutes for questions. So I have a quick question, maybe very naive, but since it's the application area is slightly different, but there's a framework called Madness in Oak Ridge. How could you compare it with ExaHyPE?
So I actually have to admit that I don't know the Madness framework. So that is for PDEs in general, or for
PDEs and the integral equations. But in terms of application, it was mostly used in quantum chemistry.
So I think what was the design choice of the ExaHyPE engine is that we really stick to a strict numerical scheme. So also if you compare it to the DEAL finite element library, for example, or to FireDrake, so these are all very flexible, or aim to be flexible in terms of which types of finite elements you are using and so on, which grid infrastructures that are using. So ExaHyPE is really focused on ADER and octree type Cartesian meshes, which are dynamically adaptive. So this is really fixed. So in that sense, it's an engine. It allows to do simulations of that kind, but then you're flexible in terms of the hyperbolic PDE. And it's really, we've been starting with hyperbolic PDEs for the time being. We are kind of expanding that, but this was really the design criterion at the beginning.
Well, I think you have asked the next question. the questions about elliptic.
Okay, can we handle elliptic PDEs as well? We have started to work in that direction. So the atmosphere physics example that I showed on the earlier slide, the cloud formation. So that is nominally going towards an elliptic case, a parabolic case actually. So parabolic PDE, I think, or close to parabolic, kind of in that area, that's something we would tackle. Elliptic is not so much, because there you basically solve the large system of equations and you're done. So this is not so much the strength about this framework. So there you would probably go for different engines or different frameworks, at least for the moment.
Okay, thank you very much, Michael. It was
Thanks as well.
and really humongous work, very interesting, lots of very important applications.